Hi, this presentation will cover using distance attenuation and spotlight effects with Phong lighting. Distance attenuation controls light getting less bright on a surface the further away the light is from the surface. Spotlight effects are where the light is shining like a spotlight, so things in the cone of the spotlight are well lit. Things outside the cone of the spotlight are poorly lit or not lit at all. So let's start with distance attenuation. It's a very ad hoc formula here. And the usual formula that's used, though, is we'll have a factor delta is defined as something like the following. Delta is 1 over k sub c plus k sub l times d plus k sub q times d squared, where d is the distance to the light from the surface, from the point X being illuminated to the light, and where k sub c, k sub l, and k sub q are constants. In fact, they're properties of the lights, so they're light properties. So C, L, and Q stand for constant, linear, and quadratic, because they're the coefficients of the constant term, a linear term, and a quadratic term in a polynomial involving d. And so basically, if you had a physically correct simulation of light fall off from a point light source, you would have inverse square law. So inverse square law would be the correct way to model light dropping off with distance from a point light source. But in fact, most lights aren't really point light sources. They're so-called extended lights, which extend over some region. And so the drop-off will not be as bad as quadratic, at least if you're in the general neighborhood of the light. And so by having three constants here, k, c, kl, kq, that are not really physically correct, do give the designer of the scene the ability to tweak how fast the light drops off. So these values, kc, kq, kl, are picked to achieve an attractive appearance in the scene, usually in a very ad hoc or special purpose way. And so this is the formula for the diminution of light with distance. And so delta, we'll see in the final board, is a multiplicative factor on the intensity of the light that will affect the diffuse and specular components of the light. So let's talk about spotlights next. A spotlight is a light that shines light out in a cone around some central direction. So think of a stage light shining a spotlight onto somebody. That's what we have in mind for a spotlight. A spotlight has a central direction in which the light is shining, given by a unit vector s, which is the direction of the spotlight, and it has an angle theta of spread. So the picture is something like the following. Here's our light. It's shining out, centered on the direction S. It's throwing out a cone of light here with making angle theta with S on all sides. We think of this shining onto a flat surface here, in which case the cone of light hits the surface and illuminates some elliptical region on the surface. If a point X is lying on the surface, inside the cone, it'll get some light from the light. If X is outside, it won't get any light from the spotlight, or at least not any diffuse or specular light. X has a unit vector L pointing towards the light. If I extend that unit vector up to the light here, it makes angle phi with the central axis S. And then if X is outside of the cone of light, phi will be bigger than theta. If X is inside the cone of light, phi will be less than theta. And we use these to define a spotlight attenuation factor of how much, which is a multiplicative factor, saying how much light from the spotlight is reaching the point X. So the spotlight attenuation factor is given by the following formula usually. I'll call it delta prime to distinguish it from the distance attenuation factor on the previous board. This will be equal to 0 if phi is greater than theta and the point X is outside of the cone of light. And the usual formula for things inside the cone of light is cosine of phi to the cosine of phi to the C if phi is less than or equal to theta. And so here C is the spotlight exponent. And all three of these values, S, theta, and C, are light properties. These are properties of the light. Okay. So let's understand what this cosine of phi to the C thing looks like. If I graph the cosine function, it looks something like this, of course. Let me draw that a little bit better. Cosine looks something like this, of course. Here's the middle 0. Here's height 1. And theta, it controls the width of the spotlight. And if phi is between minus theta and plus theta, then we're within the cone of light. And what does the graph of cosine of phi to the C look like? Well, if C is greater than 1, it'll look something like this. Cosine of phi to the C is this thing here. And this is cosine of theta. Okay, think of this as the phi axis. So this is cosine of phi. If C equals 0, and cosine of phi to the C is cosine of phi to the 0 is just equal to 1. In that case, here's the graph of cosine of phi to the 0. Okay, so what this does, if C is bigger than 1, what this is saying is that when theta is at 0, the factor delta prime is 1. So delta prime equals 1 if phi equals 0. With C greater than 0 or greater than 1, the curve looks something like this. So the light drops off more rapidly as C gets bigger from the central axis. So as phi gets bigger in absolute value, the light factor, the spotlight factor, drops off somewhat rapidly if C is big. And so what this will have the effect in that case is that, so with C greater than 1, we're going to have, or actually any greater than 0, we'll have the brightest spot will be at the middle, at the center, which is right here, and it'll be less bright at the edges of the spotlight, giving a transition from a bright center of the spotlight to a not so bright edges of the spotlight. On the other hand, if C equals 0, the spotlight is constant brightness throughout the cone. So this gives us the formula. Now we have a trig function here, and I want to get rid of it. So the nice thing to notice here is that note that cosine of phi is equal to negative L dot S. Why? Because L and S are unit vectors, and they make an angle phi with each other. The negative sign is because they're pointing in opposite directions. So we can recompute in a simpler way. We can let delta prime be equal to 0 if cosine of phi is less than cosine of theta, and equal to the negative L dot S raised to the power C otherwise. And then this is the usual formula used for the spotlight attenuation factor delta prime, because we can do it with dot products instead of having to use trig functions. So in this case, we actually don't need to know the value theta any time in the computation. We just need to know the value cosine of theta. So it's common sometimes to take cosine theta as the light property instead of theta. But of course, they're interchangeable in terms of you can get one from the other. Good. On the next board, I will talk about how to combine the distance attenuation and the spotlight attenuation in the Phong lighting. So to combine the distance and spotlight attenuation with the rest of Phong lighting, first recall that our old formula for Phong lighting was the I as seen by the viewer is the sum of the ambient lighting, IA, the diffuse lighting, ID, the specular lighting, IS, and the emissive lighting, IE. So our new formula will be the following. We're going to let the delta, the distance attenuation, will affect the ambient light, the diffuse light, and the specular light, and delta prime, spotlight attenuation, will affect just the diffuse and specular light. Okay, and if the light is not a spotlight, we'll just use delta prime equal to 1, so it would have no effect. So the new formula then is I is delta times IA plus delta times delta prime times ID plus delta prime times IS plus IE. So the distance attenuation affects the ambient light and the diffuse and the specular. So as the point that's being viewed gets further away from the light, presumably the constants in the distance attenuation value delta are making the delta drop off to 0 as the distance gets bigger. We typically want delta to be less than or equal to 1 so that we're never increasing the light due to the distance in some sense. If you get too close to the light, you don't really want to go past the factor 1. So this is typically at least. And the delta prime, the spotlight attenuation, is affecting the things the spotlight's shining directly on. It's the diffuse component and the specular component. So if we have both distance attenuation and spotlight, then both of those factors affect the diffuse and specular component. That's the end of this presentation. Thank you very much.